And floor is yours.
Thank you.
Thank you very much for the kind introductions. So actually, I have two introduction slides, the one with the initial title, and we have another one to. We are both from the same department, the Material and Process Department of Safran Tech, which is the corporate research center of Safran located near Paris. The initial title was about computational alloy design, and then while making the slides, we decided to go a bit more on the fun side, so it's going to work. Yeah. This is something I hope by the end of this presentation you will get, hopefully. The thing is, we've directed the presentation more about the ins and outs of material space exploration with a few examples that will make you touch the reality of application at Safran or other previous applications. So, the presentation should last about an hour. And we'll go first through, well, not about us, because you just presented us. So we'll talk a bit about the group we belong to, so as to give example of application that we have, which are very numerous. And then we'll talk, and this is the main philosophical part of the presentation, we'll talk about combinatorial explosions in material design, which I think is a very part of material design that influences greatly the way that we think about modeling and machine learning and decision making in material science and material design. And then we'll go through a few examples. I've listed three, I have one more. So I'm mainly going to explain things on nickel-based superalloys. Then I'll go through high entropy alloys design, or complex concentrated alloys as they came to be known. And then we'll talk about electrode coatings. Marjorie will do this part. And then we'll give a few outlooks, which I would be very happy to discuss with you in all generality. So I'm going to just say that the work we're going to present here has been done in a lot of laboratory with a lot of collaborations that I'm not going to mention it, but I'm going to present some of my PhD thesis work and postdoc work. So I have been far from being alone in this. So, but I'm going to just switch that if you're fine, because I think we all know. This is an actual picture that my PhD advisor used at a previous conference. So I guess this one could have been put in place. So I'm going to let Marjorie do the introduction of the group.
If you want. The idea is just to give you a brief overview of our group. It's something quite big. We are working in aeronautics, space and defense. So just a few figures. I won't go through everything, but as you can see, we mainly make some aircraft engines. We are very well known for this, but also helicopter engines, some landing gear, some interior for cabins. We also work with everything about drones, for example, and also some space surveillance. It's maybe not so well known, and high performance optics. So we did some optics for the very large telescope, for example, or for space telescope. We are a French group, so really French. We are. You can hear it with my wonderful accent, I know about it, but we are around 83,000 people. You can see almost in 30 countries. What you can see is that in Europe, we are more than half of the group in Europe. And when we say in Europe, most of us are in France. We have some people in UK, in Belgium, in Spain, and so on. But the big part of the group is in France. That's why the corporate research center is in France. But we are almost worldwide right now. Just want to show you a few slides about Safran in France. As you can see, we are almost, let's say, everywhere. There is not everything. We have, I think, 300 company or location in France for Safran. So everywhere you go, you find somewhere Safran. Safran is here. But we are also in Canada. So that's why we have a lot of collaboration with Canada, because we have some employees in Canada. Most of them are in Quebec, but not all of them. You can see that we are in Mirabel, Kirkland, Ajax, London, and Peterborough. So let's say almost Toronto. It's quite far away. I tried, it's quite far away from Toronto, in fact, but it's some big company of the group. As you can see, electronics and defense. We have also a landing system in Ajax, Safran landing system and Safran helicopter engines. Our colleagues that are more recent in our group, Safran Cabin, maybe you know them as Zodiac. We just bought Zodiac Group in 2018, I think, something like this. But so now we have also everything about cabin we didn't have a few years ago. Just a few overview of our product. We work mainly on aircraft propulsion. So when we say aircraft propulsion, it can be aircraft engines, helicopter engines, but also nacelle and engine equipment. What you can see on the right of the slide is a power transmission for engines. So it's quite an important part of the engine. We have also some aircraft equipment, so landing system. When we say landing system, it's both landing gears, but also wheels and brakes, so carbon brakes, for example. Everything about electrical system, I didn't put the slide here, but there is one I like that is saying that in a traditional commercial aircraft, you have around 500 kilometers of cables. So it's just huge. We know how to organize, to put everything as it should be together. And something quite funny also is to know that it's just people doing by hand. Everything is done by hand when we speak about wiring in an aircraft. We have a big activity on avionics and electronics. So everything about guiding for military aircraft, for example, but also for commercial aircraft. And when we say aerosystems, it's safety equipment, for example. So the slides, for example, it's also made in Safran. For a few years now, we have what we call aircraft interiors activity. So you have everything about the cabin, everything about seats and passenger comfort, entertainment. So maybe some fun facts when we say cabin. We have everything in the cabin, but also galleys, toilets, water management. We say water management, not toilets, but we also do toilets in. Okay, somebody needs to do it. And if we have a look to defense activity, everything about navigation and guidance. So for aircraft, for boats, for example, can be for almost every vehicle, in fact, depending on the precision of the navigation and guidance we need. We have a lot of optronics for soldier. Drones and robotics. So there is one drone that was fully developed by Safran. That is the first French drone. Up to now, we were using even in our army American drones because we didn't have our own one. What we call dismounted warfighters. Let's say everything that will help a fighter when he is really all alone with nothing to help him. And we have some guidance solution for missile, for example. If we move to space, we have everything about launch vehicles. So it's through a joint venture. Before it was everything in Safran, and for I think 4 or 5 years now, it's through what we call Ariane Group. We have a very specific activity on satellites that is very it's all about plasma physics, so I can speak of plasma physics here. It's very, very nice. It's what we call a plasma propeller for satellites. So we have the very small one, only for positioning in space, and right now we have bigger one. When you launch using your rocket or whatever, now we can use only electric plasma propulsion to go to the right place. So it's something very new. The first one were launched 1 year ago for some defense application in France. We also have a lot of work on ground station and how they communicate together and with space. And I just told you a few words about it, but everything about space optics. So we have a small company totally dedicated to space optics in our group there in France as well. Just to show you, I won't comment at all. I have 4 like this, I won't comment. The idea is just to show you in Safran, we do, let's say, almost everything in an aircraft, but the aircraft. So everything inside, it's us. The aircraft, it's not. It can be Airbus, Boeing, or whatever. But we have really plenty of products with a very different technologies, materials, application. If we move to commercial, helicopter, as you can see, it's almost the same. So we can see some funny things such as flexible tanks, for example. So on one side, we are going to make very specific metallic materials, but we also work on very specific polymers, for example. And we have the same for military helicopters, as you can see there. And if we move to military aircraft, it's the same. We do also very specific engines for military aircraft. In France, our military aircraft are wholly French. So the aircraft is from a French company and almost everything inside is from Safran. Just a few figures only about innovation. I won't tell you about revenue of the group and so on. I think it's not so interesting today. But those figures, you can see what we invest every year in R&D. It's quite a huge figure, really huge. Something that is not written here is that it's around 10 to 12% of our annual revenue that is invested each year in R&D in our group. So it's quite impressive. The second figure about employees in R&D is also interesting to comment, I think, because we have a way to do that is quite special. When you see this figure, not everybody is fully working in R&D. It means that a lot of our colleagues in business units, for example, are partly involved in R&D, part of their time. So they can work on whatever you can think about in the factory, but 10-20% of that time is dedicated to R&D and working on R&D projects linked to their work. So it generates a culture of R&D in the group, in the whole group, all over the world. As you can see, the big part of our budget in R&D is dedicated to environmental impact of air transport. So it's not new. It's not since the COVID crisis. It's very, very old, I think. I always saw such figure for 10 years. I'm in the group. You have also the number of patent applications we filed last year. In France, we are the first patent deposit in France for 2 or 3 years now, and we are in the 5 main for more than 10 years. Just 2 slides, I think, on decarbonization of aviation, because, of course, it's our target. we need to contribute, of course. I just would like to take a little time to comment this one specifically. We are, let's say, between 2020 and 2025. Due to the increase of commercial flight and so on, we know that we will have more and more commercial flights and commercial aircraft. So if we do just nothing, it won't be possible. There are several ways to reduce CO2 emission. And here we just put the various contributions. We try to move to, let's say, disruptive technology. What is behind this? Our last generation of engine, it was CFM. When we moved to the LEAP engine, that is a brand new one, we reduced fuel consumption by 30% and noise by 50%. We are now working on the next generation. We will do the same for the next generation. So with 2 generations, you can see that we really drop everything about fuel consumption, noise, and we can speak also about CO2, NOx, and so on, everything that goes with it. What you need to know is that when we start to work from scratch on an engine to move to when it is going to fly, it's 30 to 40 years in commercial aviation. So everything takes time. So to reach such figure, we started to work on it 50 years ago, something like this. We have a small part that is on operation improvement. It's something that should be just basic, but sometimes when we arrive on an airport, you have to make 1 loop, 2 loops, 3 loops before landing. We have some solutions to help managing this and trying to, let's say, decrease it as much as possible. The big part here is sustainable aviation fuel. We are convinced that at first, before hydrogen, for example, it will be a large contribution. So we are working on it. We have a very big expert on this part in Safran. We have different things we are looking at. So some of them are already available. Some of them are not available, but we are working on new ones. So we really think that is the big part of the work. And the last part you can see in black, it's offset and negative emission. It means that we think that 5 to 10%, we won't be able to not produce them. So we will have to make some compensation or whatever, but there is still a little part we are not able to not produce to go to zero net emission. So we won't go to zero net emission. We will go to minus 90%, and the 10 remaining percent we will try to compensate by different ways. So our roadmap in 3 main points. First, we want to move to ultra-efficient aircraft. It means that we need new engines. So the brand new one is 2 years old. We are already working on the next one for years and years, in fact. We want to decrease fuel consumption, of course. But we also need light materials, because if you want to decrease fuel consumption, you need a wonderful engine, of course, but you also need to be lighter and lighter and lighter. We also move to more electric aircraft. What I mean there is not that we are going to put batteries and we can just take off on batteries. It won't work for very long flight or whatever, but for example, on commuters, it can be an option. So we are working on those options. We are also moving to low carbon fuels. So it can be low carbon fuels, but something that is also, there is a hydrogen solution. So as you can see, it's written hydrogen solution and not engines. Right now, we are working mainly on fuel cells because fuel cells can be used right now in 2-3 years as auxiliary power units, for example. They can be used on ground. To move to hydrogen engine, there is a lot of work. We can do it, we work on it, but it will be, let's say, later. And the last one is to use electric or hybrid propulsion. So we are mainly working on hybrid right now to move to fully electric for helicopter, commuters, regional, not long commercial flight. We won't be able to do it. What we target is less fuel, better fuel. We will try to achieve it.
So with this explained, I think that you get why material development is of importance to the group, because a lot of improvements come from the improvement of the material that our products are made of. Now, material development is not an easy task, obviously. The way we're going to present that, I told you, is through combinatorial explosion. And I selected a quote from a work of a few years ago from a company called Citrine Informatics that I like a lot. And I think the question they're asking is very relevant to us, which is that, and you're going to see it, that the space of all possibilities is so large that the question is more, the first question is more, where do we find the interesting materials? And the second is, how do we find them? And so finding the right A stack is a task in itself. And the way to show that, I think, so it's very naive, and you're gonna have to bear with us. We're gonna take an example from the point of view of the chemist, would say, and another point of view from physicist. I do alloy design, and my playground is that. This is the playground of most of us, anyway. And the way you can introduce alloy design is through the edges. The first one being bronze, so which is a mix of copper and tin. Then you go on later to the mastery of iron and steel's metallurgy, which played a crucial role in the Industrial Revolution, for example. And then much more recently, you can trace back the invention of the discovery of stainless steels, also steels with chromium and nickel. And they were used in aeronautics for a time, but quickly showed some limitations. And so were introduced superalloys. And then you can see the start of something complicated. So if you have nickel-based alloys, but you also have cobalt-based, iron-based, and you have a mix of the three based. And then much more recently, some crazy people said, why do we need a base element when we can put approximately the same amount of each of them? And this is the start of what was initially called high entropy alloys, and which has become known as complex concentrated alloys. And I mean, there is complex in the name, so it's difficult. The thing is, you can make these alloys with a very large number of components, and even pruning the space of all possibilities by selecting only alloys with at least 5 components. Say you create alloys based on 50 elements, and each of them has 50 possible values, 50 possible weight percents. And that's not far-fetched, because that's like from 0 to 5% by steps of 0.1%. And a step of 0.1% is very realistic, even in industry settings. And so you have already a lot of systems, 10 to the 15. You have even more number of alloys, which is the pure combination of our alloys. It's a simplified calculation, but bear with me. And the thing is, the philosophy of that is that you can tell yourself that comparatively very few alloys have been ever elaborated, produced, and tested, even fewer actually. And I always say about 10 to the 6 million alloys, which is a figure that we put out of heads. I never calculated that. But the ratio between the two lets you see the complexity of what we're dealing with. And actually, it's can be even more complex, because what Marjorie does is ceramics as well. And you can think about complex concentrated ceramics where you add nitrogen, oxygen, carbon. And so it complicates things a lot. So you have a bit more order of magnitude. This is ridiculous. And this is even more ridiculous since you can consider that even fewer ceramics has been made, and even fewer are reported in the literature. So it's a big problem. Now, from the point of view of physicists, that we were talking about composition, but that's only half of the situation. The other half is process, because the chemistry does not give you the properties. You have to have process, and the process is.
We just took an example in plasma physics, because I mainly do plasma physics. I know a lot of you knows about plasma, so I will be very short on this one. But in a plasma, you have a lot of things. You have neutrons, you have atoms, you can have molecules, you can have both of them, of course. We can have radicals, ions, positive ions, negative ions, electrons. You just mix everything. Each population of them has its own energy distribution, temperature, velocity distribution, of course, and chemical reactivity. So we can see a lot of combination right now. And if you move to, let's say, a more macroscopic level, we know that the plasma is globally neutral. So I just told you there is almost everything, but let's say it's globally neutral. But it's also sensitive to electric fields and magnetic fields. So what we can guess is that we have lots of parameters, lots of correlation, but it's not so easy to measure everything. Some of them are almost impossible to measure accurately. So if we took this from really, let's say, the basic plasma parameters I have when I am in front of my equipment, I just want to make a plasma in my machine. I have pressure. Pressure, let's say I work in low pressure plasma, so let's say 0.1 to 10 Pascal. The gas flow, I work on an equipment, I can move from very low gas flow, 1 ccm, to very big one. When we say gas flow, we need to think that we have a neutral gas to do the plasma, let's say argon, for example. But I can also use some reactive gases, and I can put 1, 2, 3, 10 if I want. So a lot more values to add. Let's talk about temperature, not atom or electrons or whatever, but just your substrate temperature. You can just work from room temperature to, let's say, 400 degrees. We can go higher if we need. It was just for the example. Then one very basic parameter is target power. I do PVD, so physical vapor deposition. I just have a target. I put power at the back, and it gives me something. I can go from, let's say, 5 to 200 watts. It's not very big power, to be honest. But if I want to do some complex alloys, as Edern showed you just before, I need one target per material. So if I need 5 materials, I need 5 targets. So the combination of all of this for 5 different targets. I can also just use the distance target to substrate, because it's going to change the microstructure, so the properties of my materials at the end. And if we make just a quick calculation, you can see that we can reach something like 10 to 24 discrete values of sets of plasma parameters only on my equipment, so only the one I have in my lab. I don't speak about all the equipment of PVD you can find everywhere. So if you add this to the combination of material you saw just before, you can see it's just insane, in fact. I can just imagine what it means. So here again, I have a lot of parameters, some correlation between, for example, gas flow and pressure, depending on my pumping system, for example, depending on the vein or whatever. So from one equipment to another, there can be correlation or not. It will depend on your equipment. And some of those parameters are very difficult to control, or some of them can be controlled, depending one more time on the machine you are using. And now, I love PVD. It's very nice, but I prefer IPIPS PVD. So IPIPS is for high power impulse magneton sputtering. So it means I do conventional PVD, but instead of having a DC power signal or a pulse power signal, I will use the famous IPIPS signal. It means that I have a lot of parameters to add to the previous one. I can work with pulse duration. And as you can see, pulse duration, we can move from 1 microsecond to 5,000. One more time, it depends on your electronics. So you can do even better than this. We are going to try to play with duty cycles. So from 1 to 100%, meaning when I'm around 100%, I move to DC. But we can do the whole thing on the same machine. We can play with frequency on actual equipment. We can move from 10 Hertz to 10,000 Hertz. And the most funny part of the work is to play with applied voltage. So as you can see, we can move, let's say, from 100 to 50, 100, something like this. If we add all these parameters to everything we saw before, we have a combination of material possibilities and plasma parameters that is just, it's ridiculous. It's really too big. And the most important point is there to understand that each point can be a specific material, meaning I will have maybe the same chemical composition, the same microstructure, but not the same texture. See, if the texture is different, final properties, functional properties will be different. So it means that the space of possible for me could be this, in fact. The good point is that in this huge space, a lot of things are not interesting. And I won't be able to explore everything in my whole life. No, I'm already too old for this. Another point I just want to mention is that all those parameters can be recorded, but some of them can be reached and some of them can be managed, meaning you just see what you get. And as I told you, the final properties of the thin films are directly linked to those parameters you have to add to the chemistry before. I think the next one is yours.
Yeah, the next one is just a summary of how big I don't know what it is, but it's a pile of phase stack, but it's like you have a bunch of pile of phase stack and you don't really know where to look. I just put this morning the age of the universe converted as octoseconds or femtoseconds, just to give you an idea of what the percentage means. And I find interesting, as Marjorie said, not all materials are interesting or even possible. So it's a very rough approximation that we should obviously. But I think that even with corrections, the number of the possibilities are so huge, are so numerous that there must be some room for improvements. And I would just say, I'm going to show you example on nickel-based alloys, and we hear few times a year people saying nickel-based alloys are done. I mean, even without going to such exercise, such length, you can find that we can do 10 to 10 alloys. So it's not possible that we have explored everything at the ID. So there's room for improvement. The question being, how do we exploit this? And I think I see the time flying. I think we're trying to accelerate. We just showed you something which is very philosophical. Now we're an industrial group and we have industrial challenges. And I think you get the idea that we have to improve the performance, but we also have plenty of other criteria when doing our design. We have to keep costs down. We have to keep the materials as repairable materials or repairable parts. We have to comply with evolving regulations that allows you certain materials that forbid you some other. And we have to keep in mind that the engines must go out of the factory in time. And this has a whole lot of implication when doing alloy design. We will touch that a bit later. I'm not sure this is essential to the presentation. No, the idea is that I will just emphasize on what Marjorie said earlier. The time of development in aeronautics is very long, and we're talking about 20, 30 years of development for material, for example. The way this is, the maturity of a technology is ranked is through TRL, and actually, and this is, we're going into the details, but this is where computational material design can help by going faster through this TRL level. And this is an example from, you might be familiar with, from Quest Tech Innovation, which is a company based in Chicago, I think, at Northwestern University. These examples are about two steels, and they show that by using as much, I won't go into the details, but by using as much modeling and simulation as possible, they were able to compress the time needed to go to higher TRL. And this is the idea we're aiming at, and actually there is a whole ecosystem like the MGI in the US, the Material Genome Initiative, launched in the early 2010s, that involve this integration of experimental tools, so the traditional way of doing things, with more recent tools like computation, more modeling and simulation, let's say, so conventional computational tools. And then the last part, which is where we see artificial intelligence through the lens of data-based models, from data and empirical-based model. It is interesting to note that the situation is quite similar in China, which I will leave you the slides. You can read. The author is a member of the Academy of China, and they basically copied the MGI and adapted it to China. This is what the graph shows. I'd point out that the funding for material science in China has been increasing over the years. The graph shows this is from about 2 years ago, but I think the trend would be the same today. I just mentioned that in France, 80 million euros projects, a similar project was launched last year. So now, when talking about material design and particular our design, we usually do present the usual triptych of material composition, microstructure, and properties. The process is hidden behind the microstructure, this simplification. So the usual way of doing material design is, I would say, and this is very simplified because we don't have much time, but the usual way is doing the composition to properties, and this is the guided by science way of doing things. This is serendipity sometimes, and it's perfectly fine because I mean cars are running and planes are flying, so that works, and that has led to the development of very successful alloys. But now you can see 10 to the 18 5 alloys on one hand and one use case on the other end, and you can tell yourself, isn't there a more efficient manner to design an alloy? And I think the way, well, I think an awful people think that you can do the guided by product approach, which is the alloy by design or material by design way of things. And the idea is that you know your application well because you know your product well. So you can select a very limited subset of the space to guide you. And by knowing the properties that you're interested in, you know which one you have to model, typically, and which one you have to have data for it. So yeah, just another thing. Going from properties to composition is theoretically sound, but what we need is to screen the space of all possibilities to be sure to find an actual material. And so to do that, we need to link the composition to the properties. We have to get the composition dependence of the properties, which is rarely seen in the literature. And so what we see, this is very simplified, and I hope you will pardon me. There's plenty of modeling techniques at different length scales and time scales that works well. I'm going to simplify things and say what I'm interested in as an industrial researcher is macroscopic properties and even more performance, which is related to properties, which is more macro. And so I would like to go from, I think I got it, composition to performance. That's what I would like to do. But at the moment, you can't really predict, say, mechanical resistance with DFT calculation. That's not possible. So the idea that our philosophy is to use multi-scale modeling where it is relevant, but then achieve quick wins by avoiding the description, the physical description that are needed for macroscopic properties. That's a simplification. And there's a lot going on in this. This is really, that could look bad, but there's an example that shows that it can work. And so this, I'm going to accelerate. This slide will come to the end as well, but this is really where discussions is welcome, because this is opinionated. This is opinion. The way we introduced this concept at Safran was through methodology, so which we call numerical methodology. So looking at the left-hand side, you have something that I think looks rather logical to you. We have data. If we don't have data, we generate them. Once we have data, we use them for assessing physics-based model or data-based models, depending on what I just said before. And then once you have validated these models, you can use them for optimizing composition or processes. And once the optimization is done, you have to validate what you've predicted is as interesting material or process parameters. And so you have the whole synthesis and testing part. Now, there are authors that classified the different paradigms in material science from the first to the fourth. So the first being purely empirical science, going to model-based and then computationally based, and then big data. Big data. There's no real big data in material science, but and the idea that there's no replacement of the previous paradigm. There's just a completion. There's just assistance from machine learning. But I would like to insist on the fact that I think machine learning can help on the four axes that are here. Either the data acquisition, the modeling of this data, the optimization, which is machine learning sometimes, and the validation as well. And so you have a bunch of concepts that will come back later, but that are current research interest in Safran or our partners. So I'm going to go through the first example, and this is an actual joke from my PhD advisor. So you know why I do jokes now. So just as a quick primer on nickel-based superalloys, they're used a lot in gas turbine because they have excellent microstructural stability, environmental resistance, mechanical resistance at high temperature, and high temperature high enough that titanium alloys or steels cannot be used. So they are either used for the discs, but also for the blades. And blades are subjected to really high temperature and really high mechanical loads that make nickel-based alloy at the moment the most realistic options for this for these engines. And so this motivates the development of novel alloys. And as I showed you in the introduction, you can see that they're increasingly complex alloys in terms of composition, with the addition of more and more elements. But they are also, from a processing point of view, increasingly complex alloys. And it's just a way of saying from 80 years ago, they were cast and wrought alloys or parts. Then they became purely cast parts, and then directionally solidified turbine blades became available, which you can see here on this photographic image. So you align the grain boundaries to have better creep resistance. And then the next step was logically to remove completely the grain boundaries because they're detrimental to creep resistance. So it became the single crystal superalloys. And they are very different materials from other nickel-based superalloys. And this has some nice implication. As I showed you in the introduction, lots of elements, each of which has its own role, either on solid solution threatening or precipitation threatening and grain boundary threatening. Then you have environmental resistance. The idea that you have to play with a lot of elements. Nickel is a very accepting element, so it makes things harder. But what you're looking for basically is in this phase diagram, this is the aluminum and nickel phase diagram. You're looking to have a gamma matrix with a gamma prime Ne3 Al Pi, etc. Precipitates, which you can see the distribution that we're aiming at for these alloys with cuboidal gamma prime surrounded by channels of gamma. And this is very resistant microstructure to creep, to dislocation progression. So the design strategy, I'm going to go over rather fast. The idea is that usual triptych. What we did was not link composition to microstructure, but we used CalFAT, so calculation of phase diagram methods, to get information about the constitution. There's no geometrical aspect to this prediction. It gives you the evolution as a function of temperature of the phase fraction, and it allows you to see if a composition is a gamma prime alloy or if it contains other phases that you don't want to have. And then, as I said before, the idea is that we don't really know how to go from there to there with physical model, with a full chain of physically informed models. So what we do is regression, as very well. This is I have a colleague that says that machine learning or deep learning is glorified regression, and I think this is right. But now for regression, that works well, but you just need data, and so this is where bibliographical study come into play. There's no miracle, you know. And so what was done during this work was a study of about 500 patents, and that led to the construction of a database of about 2,000 lines for time to rupture. That's where was about $600, which is pretty good. That took about a month to do, and there were other properties of interest that's not only quick life, but that can be. What you can see is that it can be quite a nightmare because you have a graph in Japanese, you have tables in Russian, and a whole bunch of languages. But these patterns are a very interesting source of data because they compared to the scientific literature, because they have less constraints, I would say. And I was very surprised that you can find so many information and patterns. I'm talking about pages long of creep rupture time given by manufacturer of nickel-based superalloys, which you could never find in a paper. So you do validation once you have your model. I'm not going to go into details. If you know the R2, the Q2 is approximately the same. It's a little bit more stringent. And the idea that you can have a model that works quite well, that you can see graphically or that you can validate numerically. We had a precision of about 10% with this model. So it's realistic given the usual error of measurement of these properties. So once we have the model, then we have the composition dependence and we can screen large spaces, and that's what we did there. So you have the boundary of each elements there. They are very broad for nickel-based alloys, and the step that we defined for each of these elements defined a space of about 300 million alloys, and we had a bunch of criteria. The these two were from CalFAT calculation. This one was from the regression model. And then the last three were just rule of mixture or empirical models that we could find in other papers. And so we screened all these alloys. The most, and that's what I love this morning, because CalFAT calculation are long. You know, it's 200 milliseconds. It's long. For us, it's long. So it took 50 days for approximately 50 million thermodynamic behavior, because you apply a strategy where you do the cheapest calculation first and then the costs later. And you have some results there. On each criteria, we put specification values to attain. And we had about 200,000 alloys that complied with the specification. And those are represented here. So on the left figure, the y-axis is the creep resistance at 950 degrees Celsius. So the higher, the better. Density is on the y-axis, the x-axis, sorry, and lower is obviously better, because lightweight materials tend to resist more because they have less stress applied to them. The hexagons there are the 200,000 alloys that's binning, that hexagonal binning, and the number of alloys is the colors. And what you see in red is the existing alloys from the database. And I always found this graph nice, because the position of them compared to the position of what we screened showed an increase in specific creep resistance. So it kind of shows that, numerically speaking, the margin of improvement was indeed exploited. The graph on the right show the creep rupture at another temperature of interest, and the density as well. But now the color is the mean gamma prime content of each alloys. So the gamma prime phases is what imparts the mechanical resistance. And I showed you before that the CalFAT model and the Gaussian process model do not communicate to each other, so they can kind of diverge. But what is shown here is that most of the time there's a lot of alloys, so you have representation effects and overplotting and a bit of problem there. But most of the time you can find that the most resistant alloys are the one containing the most gamma prime. And for two models that did not communicate, that's a good result, because it means that the physical prediction from the CalFAT calculation correlates with the database approach, which is reassuring, which is not always the case. And then you could talk about this little point there, but will not. So then 200,000 alloys is a bit too much. So we try to, and I'm going to accelerate, to select through non-deterministic sorting, which is similar to what is used in genetic algorithms. And I'm going to talk about genetic algorithms just after that. So for the record, we validated prediction on these alloys for most of them, not all conditions, not all temperatures, but generally they gave us very interesting alloys with mechanisms that we did not expect they had. I'm going to go over that quite quickly. I have to explain that because there is graph. So what I showed you before is systematic search. It's a basic grid search for the space. But before that, and this is my PhD thesis, we can imagine more brighter ways to do that, and to sample the space, but not completely. And genetic algorithms and meta-heuristics in general can help do that. And the comparison to alloy design, well, you're going to see it. So genetic algorithms work the same as the theory of evolution according to Darwin, basically. So you start with a population of giraffes that contains individual with short necks and individual with long necks, and the shortened necked individual cannot easily reach their source of food, and so they tend to die earlier than the other individual and tend to reproduce less than the longer necked individual. So over the years, you find that the population of giraffe evolved to something that contains only individual with longer necks. That's the idea. And the parallel to our design is quite obvious. You can say that a giraffe is an alloy, actually, and that the leaves of the tree that they have to reach to live are the specification for your application. And so you're trying to make the neck of your alloy longer for them to be better. And there's very easy way of implementing that. They're really easy algorithms. You consider an alloy element as being a gene, so that an alloy becomes an individual. So it's a group of genes, each of which is an element, and then you maintain a population, which is a group of alloys. And there are two operators, genetic operators that you can apply, the mixing one and the random one, to make things short. The mixing one makes you choose two good parents, mix their gene and hope for children which are at least as good as their parents, which is sometimes not the case, but in this world we can discard them. And mutation is a lot of randomness, random selection of an alloy, an individual, random selection of a gene of this individual, and random changes to this gene to avoid genetic drift. So this is to avoid local optimum. And so we use that. I'm going to go that you iterate this process for a long time. I'm just going to give two examples. The first one is on nickel-based parallels for tube and disk, and this was done with a company called Edern, which is a maker of nickel-based parallels. We showed that in a space of one of their patents, we could find a material that was cheaper and better, with better temperature capability than the one that they designed using this procedure. And that was really experimentally tested in the same condition. So that was a really interesting project, because even in a patented space of computation, you can find 10 to the 10 possibilities, because they're juridic document, they're legal document, they're not scientific papers. So, and I'm just going to conclude my part, and then I'll let Marjorie on Earth. Complex concentrated alloys. Just two examples. The idea was to find alloys with single solid solution. That was our goal, because that was the original definition of a high entropy alloys. Don't ask me question why we would want to find a single solid solution. That was a bit of a hobby at the time. And the idea is that we had a probability criteria that is well described in this paper, if you're interested. That tells you, based on composition, the probability of finding a single solid solution. And so we applied that together with two other models, rule of mixture model for density, very simple. And we had another for solid solution hardening. And so we entered that in the genetic algorithm, and had 7 alloys made, 2 of which I'm going to concentrate on. The first one is a BCC alloys, validated as you having a very stable microstructure with very large grain, a single phase microstructure as well. And this alloy was very interesting because it featured a specific hardness, which is very, very high for its category of alloy. So this alloy has basically no ductility at all. It's not of any use for structural material, but as a curiosity, it's very interesting. And the other one is approximately the same, no other contribution to hardening than that of the solid solution, which is that there's no grain boundary, certainly, or very little. There's no precipitate. There's just pure matrix deformation. And so our alloy is there. It's the red square, and same as before, be it in terms of hardness or UTS, YS is compression testing. We had something that was whose specific properties were better than that of comparable alloys. We had a lot of experimental invalidation, basically 4 out of 7, which means we're not very good. But for a budget of 7 alloys out of the 10 to the 85, this is still an achievement, I think. And we're going to conclude with the nitride coating design.
Yeah. So let's say I live in a very different world from my colleagues. We don't use computer science, but we have a lot of experience and a bunch of luck, to be honest. So we look for very specific materials. I just want to present you 2 different materials. We are always working on IPIMS, so IPIMS PVD. And we found something quite funny. When you use IPIMS PVD with a beetle, we speak about tantalum, and you just add nitrogen. So tantalum nitride, something that almost everybody knows. You have the phase diagram here, and what you can see there is the very slight blue part. This part is just a metastable state of tantalum nitride. If you know how to use your IPIMS PVD, you can just stabilize and get this hexagonal phase, tantalum nitride, stable, and it stays stable. It stays stable from room temperature to 2000 degrees. And the fun part here is that, as you can see, it's a ceramic. But this one is very specific. It conducts electricity. We don't understand why right now, but it's working. So we call it unique coating reactive nitride for 2 reasons. The first one, it was because it's very funny. The second one was my PhD student was really fan of licorne in French. So we just do it for her. But what I want to underline here is that with a very specific combination of functional properties that are usually conflicting in usual materials can be found in what materials if we are able to move from what window at what from experience we would say it's not possible. At the early beginning, everybody told me a ceramic is non-conductive. It is, it's not, it is. I didn't put everything, but really it is. And it is more conductive than gold, just to give you a few figures. The second point here is as we manage our machine, it's very reproducible in different equipment. It means that we started from a small lab equipment and said, oh, okay, it's just magical. We can do it. But then we moved to a bigger equipment. It took us 3 weeks to get the same thing. So it means it's not just luck. We are able to do it in different machines. So it's wonderful. But it opens the door to a lot of questions. The first one is, why does it work? I really don't know why it works. So I need to find the answer to this question. The second one, and I love this one, is if I found this one, is there any other that could have, let's say, funny properties or very different properties from usual materials? So we tried, of course. And we moved to a second, let's say it's a metal nitride. Still working on IPIMS because I really love my IPIMS. We can do a lot of things with it. If we have a look to the literature review concerning this nitride, we have 3 phases that are reported. So the first one is cubic. It's, let's say, the normal one. Everybody can see it. The second one is the tetragonal one. It's predicted by calculation, and it was observed only 1 time by phase transition at very low temperature. And as soon as you go to higher temperature, you have the reverse transformation. So it's not stable at all. And on top of it, it's not in the phase diagram of these materials. The last one is the hexagonal one that is predicted by calculation, never observed from what we know, and also not in the phase diagram, where I can say I do magic every day and I'm very proud of it, is that we observed the tetragonal phase, but we stabilized it. So right now, using I-beams, we are able to deposit thin films of this material in tetragonal phase, stable. It doesn't move at all. You can do whatever you want, it works. So at the early beginning of the project, we called him the great HiFi nitride. But as you can see, this is not HiFi anymore. It's very reproducible, and we did it also the same in two different equipment, a small one, a lab one, and a bigger one in our industrial lab. But I still have the same question. Why does it work? And the last question on all this work is, if I was able to find a unicorn and a graphene, what can I find? Something else. It must exist, but I don't even know where to search for right now. That's why I'm working with him, because I hope he will be able just to tell me you need to go to this forest or this wood or don't know where to find maybe some more, I don't know, some mythical beast. But it's a joke, but not really a joke, in fact. Those materials have very specific properties. Today, at the beginning of the characterization, we found that they have properties we never seen before, optical properties, for example, electrical properties. So it means that there are some areas in materials with properties that we don't even think about, but we can reach them. But right now, the space is so big that I'm not even able to think about all the things we could discover and we could do. So we need help for this. And we saw the figure at the beginning of this presentation. We won't be able to try everything. So we need help to just have an idea of the direction. At least it would be very nice. So that's why now we need, I'm convinced, to put together people from computer science and people from material science, people from processes. Don't forget about processes, because we need processes also.
So I think we can. How much time do we have left? We completely blow it, or fine?
You have to.
Okay.
15 minutes.
Okay. We can talk a bit about limitation. This is actually a slide that we didn't take much time to finish because the week was full of experience. I'm going to talk about a few technical limitations. Obviously, there's a lot in the approach I showed you, and this is why I think the discussion with Kobe could be very interesting, because we don't do a lot of physical modeling at Safotec. We don't do much molecular dynamics, for example, or DFT, which is a clearly a missing point in all these methodologies that could really well complement what we do. But I'm going to talk about limit of machine learning, because I think it's very important. And I put an example on top. This is from a few years back, but I think it still applies to our problems. And this is in computer vision, but I think it's really the same in material science. It's very funny because these also had a model that was trying to recognize objects in picture. And if they show that the model of this picture, you can't really see that the model clearly was seeing a banana. So that was fine. And this has been seen in CCTV footage, for example, more recently, where you put a pattern, a specific pattern in the images, and the model goes wide, and there you can't see it, but it's a toaster. And I think with the very heterogeneous data that we have in material science, there's a few missteps that we could make, and that are similar to that, just not that we cannot represent as easily as in computer science, but there's lots of precaution to take when training our models with very specific data. And I'm not going to go over much of that, but I have an example in the next slide of deep learning application in material science, which is a bit specific. I'm going to talk a bit about it. But deep learning and even machine learning, especially black boxes, as the use of them asks the question of explicability. And this is something that we see when I would say traditional material, I'm going to say something terrible, but traditional material scientists do not like, and it's normal, models that are not, that they cannot explain, that we cannot provide an explanation for. And this is a very sensible argument. I'm still a bit disappointed because sometimes it just works well, and this is proven. But this is not explicable. This lacks this physical meaning. And this is a whole area of research currently that needs to be done. And then data availability, I'm going to talk about it on the next slides. Then I think we were talking about that this at noon. There is consideration to be had on the use of machine learning technique, and especially deep learning, which can have great environmental consequences. I will have in mind the number, the electricity bill for the training of a computer vision model, for example, on ImageNet problems, which is about $10 billion for the training, just in electricity. So apart from the giant bill, this is a giant consumption. And there is a question of relevance of such models for our application that needs to be taken into account as other industrial changes, because if we generalize the use of such models, then it's going to multiply. Then there are ethical considerations. We're currently talking to Microsoft for using GPT for doing bibliography. I don't really believe in it, but it's interesting. But what I don't believe in is mechanical turkey, such as the large language models, which, because there are tens of thousands of people behind it to correct its little mistakes and errors, and it's not really what I would consider a right use of machine learning. And then there are regulations to come for artificial intelligence, and especially in Europe, which could have a great impact if we ever consider to go that route. Because if in 10 years we have chosen the wrong technical solution, we will have impacted our project and delayed our projects. So we have to evolve on the technical side while taking into account things that are not very technical. And I would say this is a bit of a mixed slide, but we showed you a lot of material design, but we didn't talk about the fact that regulations currently forbids the use of some materials, or are going to forbid the use of some material, or are going to restrict it. For example, nickel-based alloy, uranium is going to be limited, or could be the way. The US is trying to impose limits on export controls on uranium that could forbid other companies to use it. It's very simplified. So there's a lot of work to be had on geopolitical restriction. We could talk about cobalt as well, which mainly comes because we use, I think, 10 or 15% of cobalt. The rest is mainly batteries and electrical device. But we do use a lot, and we, at the moment, are integrating it into the newest design of superalloys. But we have to find substitutes. which is all the level of complexity. And I will just finish this. We can talk later. As we just finish on that. I just give an example, and this is where I say that I'm looking for friends that would be happy to help me on this, because it is very basic at the moment. But I think one application of deep learning, but not necessarily only deep learning, could help with the application of machine learning in material science is through the use of it for mining, extracting knowledge from papers or documents in general. The idea being that we not necessarily looking at a system that does what ChatGPT does, for example. You input a paper and it summarizes nicely. Nicely is a nice word. It does something that looks nice. What I think would be an interesting research area, research direction, would be the use of machine learning to identify relevant pages, relevant documents in the bibliography, which is growing in an exponential way. And this actually are real results of ResNet, UNet models, deep learning models on Chinese patents, Japanese patents, and 2 American patents. And the idea there is that to do that, I trained a model with approximately 15,000 instances of composition. And what is shown is our composition of titanium alloys. But the idea is that the model might not necessarily be good at exactly putting the right bounding boxes around this composition, but it's pretty damn good at telling you which pages contain composition or contain relevant information. And between the start of the project and the end of the project, which was about 9 months long, I studied about 1,000 patents for that. There were 200 new Chinese patents. So I would have had to actually go back to this new patent and do the segmentation, the identification of all composition, which is a crazy work. And I think this is a really interesting point. There is a database creation, but there is also the database maintenance, the dating of the database. And if we keep doing one-shot creation, we are kind of missing the point, because in the long run, what counts is, I'm going to say that, it's the one that has the bigger database. So I think this is a very interesting research direction, and if I can find friends, let me know. So thank you for your attention. We're done.